Morning, everyone. Thank you for joining us today. I would like to explain today this method, which is a community detection method. If you are familiar a little bit with complex systems and with this problem, you will see that whenever you have a complex network, in biology, we have thousands of data, we generate many complex ways to understand this data, and networks is one that is important and is growing the interest in the use of networks. But if you create a network in biology, you will probably find something like this, which is basically a big mess, right? And we need to come out with some methods to make a sense of what's going on in this entangled network. And one family of methods are community detection methods. And in principle, most methods tend to look for what we call modules. Basically, modules are groups of nodes that tend to be highly connected between them and loosely connected within them and loosely connected between them. So this is possibly the most widely adopted strategy, the search of modules. And if you have tried to look for one method to create modules, you may have found tens or hundreds of methods. It's very difficult to choose what method is better, and actually nowadays it's becoming its own area of research to the point that you may not understand even the method. There is a lot of interest from the physicist communities in terms of statistical mechanics methods, and very often it's difficult to find a good method, and it's important to come out with something that we understand, and for that we need to understand the method. So my main point today in showing you this tool is that this tool is, to my taste, extremely simple compared with other methods, and I think it's the most important strength of this method. We build modules in principle because we want to come out with some dimensionality reduction. Depending on what is your background, you may have heard different jargon, like we want to coarse grain this network, we want to compress the network. But the important thing of networks is that whenever you come out with some dimensionality reduction and there is some coarse graining, we do not have only clusters, like traditional clusters like one could have with any comparison of samples or comparison of an alignment method, right? But we have also direction of information between these modules. So in a way, we are somewhat coarse graining a very complex network into something that in a different scale we can understand, and we can comprehend how the information is flowing between these larger entities. Okay, but in biology especially, we would like to move beyond modules. And a good example of this are, for instance, trophic networks. If we have trophic networks, we may have here like predators, then some primary consumers and producers. And if you note here, the links go through the different layers, but there are no links in principle between nodes within the same layer. So in this case, modules make no sense, because what we want to identify are the different layers, and in biology we tend to call this kind of groups guilds, which are loosely connected within them and very densely connected between them, which is exactly the opposite to what happens with modules. And there are not many methods, community detection methods, that find guilds. In addition, what is the meaning of a link? Very often, for instance, in modules detection, it's typically assumed that there is some flow of information between the different links. In this case, I'm showing you here a map of airports in the world and the links connect the different airports. The size of the node is how many flights are in that airport. And in this case, it's obvious that modules are interesting, right? Because we want to know how the information flow between the modules and within the modules and how they are connected. But it's not always the case that the one interaction means the transmission of some entity. In this case, for example, if we think again in biological terms, we may have one plant that has a seed, and the seed can be consumed by a squirrel, or the seed can be consumed by the bird. In this case, yes, there is a flux of biomass between the plant and the animals, but we also want to monitor the interaction between birds and squirrels, even if there is no actual flow of biomass between them. No, there is another type of interaction. So this is one interaction, the biomass is flowing, and this interaction is kind of interference. And this is important also when we move to more complicated networks. Nowadays, we're interested even in multi-layer networks, for example, in which each layer has a different meaning, and nodes may have interactions within the layer and may have interactions between layers. And these interactions are qualitatively very different. Another example could be, for instance, in this protein-protein interaction network, in which proteins are connected if there is any evidence of interaction between them, but the type of evidence may be different. And we may want to cluster these nodes depending on the type of evidence they have, not only on whether they have an interaction or not. So this means that we want to consider the quality of the links, and this can be done just considering the quality of the link. We can work with multi-layered networks. We can consider with this type of networks, and as we will see immediately, we can also identify both modules and guilds. And this is a little bit the idea of the method I'm going to present. It's basically a linkage between nodes according to their functional role, and hence the name functionINK. The method is very simple, basically just two parallel scripts that are then wrapped in R. So depending on whether you are more familiar with, if you are familiar with Perl, you can directly use it, although if you are not familiar, it's also very easy to use, but then there is a wrapper in R. And the two steps are very simple. One is to compute the similarity between the nodes in the network, and the second step is just clustering the nodes. So I'm going to show you a couple of examples of how the method works. Basically, we start with the similarity. Then we have, in this case, the node I and the node J, and I want to compute the similarity between them. And the similarity, and what we are calling functional role, is how similar they are in terms of their connections with the neighbors. In this case, the node I is connected with these three nodes. So this is the set of the node I. This is the set of the node I, and this is the set of the node J. And in this case, both nodes only share one neighbor, right? So I can compute something very simple, could be, for instance, the Jacquard similarity. So basically the intersection between these two sets divided by the union. As an input, I will need only the network, basically different rows in which I have the node 1, the node 2, and the weight of the interaction between them, and so on. So a long format list of nodes, which is very typical in complex networks. But what happens if I have different qualities, so links that are qualitatively different? In this case, I'm going to call arbitrarily these links in red positive links, and these links in green negative links. In that case, I just need to identify the different subsets for node I, the positive links, for node the positive links and the negative links, the same for node J, the positive links and the negative links. And now I need to extend somewhat the Jacquard similarity considering these different subsets. So I'm going to look at the intersection of the positive links on the one hand plus the intersection of the negative links on the other hand divided by the whole union. Okay, so now again, these two nodes have two neighbors intersecting because they are the same neighbors and with the same type of node. Okay, if I would have, for instance, a red link here, this would not be a neighbor of both. Okay, we are demanding that both of them have exactly the same quality. And for the input format, the only thing I need to add is another column in which I specify this quality. So basically one string which tells me what are the type of links that I have. If the network is more complicated as this one, here I'm going to focus, for instance, in node 1 and 3 in layer 3. Okay, then this is a link which is within layer 3. So I can specify it in this file, like node 1 of layer 3 is linked with node 3 of layer 3 with some weight. And I say that the type is layer 3, layer 3. Okay. Then node 1 is also connected with node 2 of a different layer. Same thing. I just say node 1 layer 3 with node 3 layer 2. And now I specify the connection. The connection is now between layer 3 and, sorry, I missed here. This should be layer 4. Okay, this is a mistake. But basically, the idea, I guess, that you can follow it. So I just need to specify the qualities of the connections between the different layers and what are the nodes that are being connected, specifying each node differently depending on what layer it is. Okay. And in this case, we can generalize Jacquard just by, I can consider an arbitrary number of types depending on the number of links I have. So Jacquard can be very easily generalized in this way. So once I have this similarity and there are implemented a couple of quantities, I talk about Jacquard because it's easier to grasp, but actually the default are Tanimoto coefficients, which is a generalization of Jacquard that considers weights. And the next step is just clustering nodes, okay? And here there is an example. It's a very simple example in which I have basically a node A, which has some neighbors that are connected only to it. And then node B, which has some neighbors, again, that are only connected to it. And then we have C and D connecting both. This is immediately we can see that there is a very clear structure here, right? So I compute all the similarities against all nodes. I'm showing just only those that are non-zero. And if I start clustering, the most similar are these two groups. Basically, node A against these three guys, and node B against these ones. So I join them. And here I have that these three satellites A now belong to the same group, and these satellites to B belong to the same group. But I'm maintaining A and B as distinct, right? Because they have different neighbors here. So I go one step forward, then I have C and D next, these two. And then I cluster them. And in this point, I think that it's perhaps the most clear step in which we can immediately see that this is a good clustering, because from the point of view of the roles, we have satellites of A, satellites of B, A and B that are distinct, and C and D that connect both motifs. In some algorithms, it's worth noting that, for instance, in the algorithm of Amaral, they would say that A and B are in the same group because, and for good reasons, one could say that A and B are somewhat playing the same functional role here, right? Because they are in the middle of some satellites and they are connected with the same nodes. Okay, but this is distinct in our algorithm because we will say that yes, the A and B have something in common in terms of the role, but since the satellites are different and the connections are different, we keep them separately. And then we move on with the clustering. We would join A in this group, then C and D, and then we can start seeing that this is not working very well. In this case, I'm using complete linkage. With single linkage or average linkage, things would be slightly different. And at this point, we cannot join anything else because the similarity between this group and this group is 0, okay? So, okay, we have this clustering, the similarity, we have this clustering, but the question is how I can find the optimal threshold, no, to stop. As I said, we implemented the 3 methods, single, complete, and average, that I advise you to try and to see the results and see how they work. The default is average linkage here. So how can we determine the optimal threshold? For this, we have proposed a couple of metrics. We call them partition density, and one is the external partition density and the other one is the internal. And basically, this is the fraction of realized links with neighbors either outside or inside ounce cluster. In this case, in which we are seeing that this network seems to have like guilds, if I focus on this cluster here, we can see that the external partition density, which is the fraction of links that are realized out of all possible links, is equal to 1, because all members of these groups are connected with all members of this group. So the links with other groups are all of them fulfilled. So, So the external partition density is very high. On the other hand, the internal partition density is very low because there are very few links within this group, which is not the case here, again, because here we have modules, and these links here are very densely connected between them and very poorly connected with the other group. So what we will find with these 2 metrics is that the partition density for the external one, we will have a higher value than for the internal one when we go through the different clustering steps. While in this case, we will have a very high internal partition density and a low external partition density. So these 2 metrics let us know a little bit in advance what kind of motifs are dominating our network. So we could just cluster the nodes, compute these metrics, perform some visual inspection, and select a threshold. In this case, I'm selecting the peak of the external partition density. And then we run again the clustering, and we stop at this threshold. And in this way, we will come out with the optimal partition. Of course, this is in the graph that we implemented in R. This can be done, the whole pipeline, completely automatically with the different defaults, the Tanimoto coefficient, the average linkage. And in this case, we will take the total partition density to stop, which is nothing but the sum of the internal and external partition density. So if you are lazy, you can just run the whole pipeline with the defaults and you will get the results. You can modify in the wrapper the different defaults as well, but I would advise to always have a look at the internal and external partition density. Why? This is one example. Here, I'm considering one network in which I have, on the one hand, plants which are very densely connected between them with competitive interactions. The same happens with pollinators. They are very densely connected because all of them are competing against all. But then plants and pollinators cooperate. Right? There are mutualistic interactions. So if I run the algorithm with this network, what I will find is that the internal partition density grows very fast and actually peaks exactly when I have these 2 groups separated, right? It makes complete sense, because I want to separate plants and pollinators. So if I just run an automatic pipeline and I don't care much about the results, well, I will have this, which is perhaps not very interesting, right? Because I'm just finding that I'm able to find plants and pollinators separated. However, here we can see that the external partition density is relatively high. Actually, if I remove most of these internal nodes, this is another example, the external partition density will dominate, and now I have a far more interesting network in which I'm focusing only on the mutualistic interactions, which is actually where there is some structure here. And you can see, for instance, that I have here, this is a plant, which is a generalist plant, which is connected with many pollinators, and is connected as well with many satellite pollinators that only pollinate this plant. And the same happens here with this animal. This animal is pollinating many plants, and only this animal pollinates these plants. It's also connected with other plants that are themselves pollinated by other animals, but this animal and this plant that are generalists are actually interacting with many singletons, so guys that only interact with it. And this is one specific feature of what we call a nested pattern in ecology. And only if you focus in this case with the external partition density, you will find and explore this kind of network. Okay, so I think it's interesting to have a look and explore both external and internal partition densities very often. Okay, so here you have the website of the project with the link. If you want, you can just use this QR, and this is the article. And now, before I finish, I will very quickly walk you through the website. Okay, this is the website of the project. And you have different options here. You have the installation, a vignette to run to follow the whole pipeline, and some hints to visualize the network. Here in the description, it's basically what I just explained you. The installation. If you are running Linux, that if you don't, you should. You will need basically nothing because you will have a Perl interpreter. There are some links also if you're running other operating systems. And the only need you think is to clone the repo, okay, and to give permission to these two main scripts, the one for the similarity of the nodes and the linkage. You have some fake examples to test that the scripts are running properly. So here you have some options to test. And from that, you will have here a full vignette to use the method. This is the type of data that you will need. So as I said, this is a typical long format for networks, just node 1. In this case, I have the two pools that I explained, plants, pollinators and plants, so plants and animals. And the interaction, if you have a more complicated network because you want qualitative links, qualitatively to distinguish the links, you will have to add this type column. And then you have the lazy pipeline, which basically is to use this function, which is the run pipeline.r. And there is an example in this script, the node linkage pipeline, which calls this function. So you can just use this script, modify it to run this function. Then you have the more detailed pipeline, which you can go step by step running the different scripts in Perl. You have different flags. For every function, you will find one help page where you have the description of the different flags you can use for the formats. The formats are perhaps the most challenging thing of the method. Sometimes it's a bit difficult to follow because there are many options depending on whether your node is directed or undirected, weighted or not, different types or not. Okay, so if you have problems, just let me know. But beyond that, the method is or should be quite simple to follow. When you cluster the nodes, it will generate different files. In this case, for instance, this file is the detailed clustering. So at at the step 0, I'm stopping with this, I'm joining a cluster with this similarity. These are the two nodes that I joined. So this is the classical output for any type of clustering, with the edges that are shared or the edges that are within the cluster. And finally, perhaps the most important output is, of course, the partition densities and how do you obtain the actual partitions of the different clusters. And this is just this file in which you will have for each node the cluster it belongs to. And this is the main file that you need for any visualization or representation beyond all the information that the algorithm is giving you. So in this final vignette here, in visualization, I'm showing you how you can use Citoscape just to visualize the network, which is very easy. You just load your network, and once you have your network here, you add that file, the partition file, and then you will have this network initially, and once you load this partition file, you can just find the different groups. From this, coming out with a nice network, you need a little bit of experience. If someone has an idea of how to go from this step to this step, please let me know, because perhaps this is the most boring and time-consuming step. But, well, of course, you can always neglect some nodes or some links that you don't need and just concentrate in the important information that you may want to extract. Okay, so I think we are on time, and this is pretty much it. Of course, if you have any issues, you can go to the issues of the repository. There are some frequent problems that I mentioned here, and otherwise, just go to GitHub and open an issue, and I will try to attend it as soon as I can. So this is everything.